Alright, so in this lesson we're going to learn how the basics of taking data, making a graph, doing a best fit, finding slope and interpreting the slope. So before you have some data on mass versus volume, we've plotted 5 points, we've put error bars on them, but we're not going to worry about error bars right now. And we see this data and we want to put a best fit. We already know that we don't connect the dots. So how do we do a best fit? Well, you'd get a ruler in this case because the dots look like they line up in a linear fashion, and we draw a line. So I don't have a convenient ruler here, so let me see if I can bring up the line. I'll do that one, and I will use the Smart Notebook to do that for me. Okay, so I draw in a best fit line, and from that we can see that there's a relationship between the two variables. Alright, and you should recognize this as a, let me just make sure I've got that. Okay, so we have a linear, and importantly, because it passes through the origin, it's also proportional. Relationship between two. And a proportional means that if I double the volume, I get double the mass. If I triple the volume, I get triple the mass. That's not always going to be the case in a linear graph. If it passes through something other than the origin, then it will still be linear, but it won't be proportional. Okay, so let's talk about doing something with the graph. Alright, finding the slope. So let's scroll down. Okay, so we want to calculate the slope of the best fit. And as mentioned in class, we don't want to choose 2 points that are data. We want to choose 2 points that are on our line. So I'm going to go over here to our graph. Let's go over. I'm going to find 2 points that intersect a corner. So this looks like a point right there. And if I go up further, if the pen will allow me to go up further, we're having technical difficulties here. Okay, let's choose, let's say this point right there. Okay, so let's read the values. We don't count squares, so I'm going to go over kind of like a dash. I'm going to read this point, so that's 2.75, so there's one of my y values. So 2.75 minus, I get this y value, that's 0.5. Okay, and those are grams, that's our units for the y-axis, that's a mass. And I'm going to divide it by the x value, so this is 10, 10.4, 10.8. Okay. Minus, and if I drop down here, this is 1.6, so I'll leave it to you to determine that for yourself, and that's cubic centimeters. Whoops. Okay, so we want to divide this out. So if we get out our calculator, we see that 2.75 minus 0.5 is 2.25 grams divided by 10.8 minus 1.6, that's 9.2 cubic centimeters, and we don't leave things as fractions, so if we do 2.75 divided by 9.2, we see that this is rounded to about 0.30, and I gotta keep the units, so I've got grams divided by, oops, we're having difficulties here with the tablet, cubic centimeters. Okay, so that slope means something important, and now we want to interpret that. So let's do just a little interpretation. So based on units, we see that for every gram, or excuse me, for every cubic centimeter of volume, we have 0.3 grams of mass. Now you should recognize that as a quantity called density, and we'll give that the symbol like you did in chemistry, capital D. Alright, now since we have a line, we can make an equation. And you have made equations in math. It's no different here. So let me scroll up a little bit Now I'm going to write it up in this area over here. You can just put it in your blank. So the general equation for a line, that's your next set of blanks, is y equals mx plus b. So now we just have to interpret that for this particular graph. What is our y variable? Well, if we go over to the y-axis, we see that it's m, mass, equals the slope, which is m here. We already said we interpreted it as density. So that's density times x. Our x variable is here, right there, the v. And b is y-intercept, which we see is 0. So we have an equation, a general equation that relates mass, volume, and density. Now you already know this, but this is how you can get that from a graph of mass versus volume, and that's really neat to be able to do. Now in this particular case, we could say mass equals 0.30, right? That's the slope we got, grams per cubic centimeter, times whatever volume we plug in. Okay, so this is a general equation. This is the specific equation for the situation. Okay, now, what happens when we have a graph that's nonlinear? So we have some data right here, just generic x, generic y. I haven't put units on it, so this would be y, this would be x. And we see that when we plot the points, they don't look like a line. So we don't force a line, but there is a pattern here, and it looks, if you carefully, assuming a 0, 0 is a legitimate point, we have a curve. Okay, my pen stopped there. And so we can say that there's a relationship here. All right. In fact, if you remember from algebra or geometry, we can say y is not proportional to x, as the proportional sign is proportional to x to some power, and most likely it's going to be x squared. Okay, but to verify this, we want to make this curve into a line. So if we know that y is proportional to x squared, that's not a negative, then we can plot y versus x squared, and if we get a line, then we know that that proportionality is true. So I would go back to my data. Here's my data table, and instead of having x in my left column, I would put in x squared. So if our first x was 4, then x squared would be 16. So let's call that x squared. All right. Then we would have 5 squared in here, 6 squared, and so on. 7 squared, 8 squared, and then I think the last one was 10 squared. So what I want you to do on your own is to plot x squared down here, the left column, y here, and you should get 6 points that make a line. Draw best fit and find a slope. Show your work right here. If you do it correctly, your slope should be around, this is very frustrating, should be around 3, and then you can make an equation for your line just like we did in the example above. So give that a shot, and we'll look at that tomorrow.